Welcome back, guys. We hope that you had a great time with the outreach workshop, but it's time now to start our second session of the Animal Behavior Live Conference 2025. It's Alexis Buatoir here, and I'm going to chair this session. And it's my great pleasure for this second session to introduce the talk of our second plenary, Dr. Amir Patel. Dr. Patel is an associate professor at the University College London in the Department of Computer Science in UK, and he is the head of the African Robotics Unit, a group of robotic researchers at the University of Cape Town in South Africa. So Amir's work is at the crossroad of robotics and animal behavior, inspired by cheetah speed and agility to design robots, and adding AI to monitor the health of wild animals. Today, Amir is going to talk about cheetahs locomotion through the lens of robotics. Amir, floor is yours. You can start your presentation.
Hi, cool. Thank you so much for the great introduction. I'm very excited about giving this talk, and I hope that many people find it interesting. So yeah, thanks for the great introduction. Today I'm going to be talking about my journey where I guess I tell people I became an accidental biologist. I'll talk to you about how I study cheetahs through the lens of robotics. So my journey started about I would say 2012, where I wanted to understand maneuverability. So things like jumping and acceleration, turning are going to be really critical for robotic systems if they ever leave the safety of, a controlled laboratory environment. Um, so it's interesting because maneuverability sort of has these competing requirements. Safety, obviously, you don't want to like crash into something, but you also don't want to break your limb when doing a particular motion. Economies, and you don't want to use, your entire battery to do a particular evasive turn or acceleration. Robustness is also very important because, most rapid maneuvers occur in uncontrolled, and unpredictable scenarios, for example, your foot slipping or an obstacle appearing. And then obviously agility is you want to be able to, redirect your velocity vector in the best way possible. And it's interesting because it's not very well studied in engineering literature and I would say robotics more specifically. We have a vocabulary for things like, galloping, trotting, walking. We all understand these periodic motions very well for steady state, so for constant velocity, but not so much for the transient motion. So how do we go from one state to the next? And when you look to nature, animals are incredible at this, right? And it makes sense because it's really vital to their survival. And no animal epitomizes this as best as the cheetah. So, this is some footage that my group out at the University of Cape Town collected of cheetahs, and you can just see like extremely agile motions, using multiple contact points on their legs, sliding, using the tail, and really pushing, the boundaries of what you can do with your body. So what do we know about the cheetah, right? So, everyone knows the cheetah is the fastest terrestrial animal. It's been measured at running up to 29 meters per second. And more recently, we also know that its hunting success isn't actually that it runs so fast, but the fact that it's able to rapidly maneuver. So, some work by Alan Wilson at the Royal Veterinary College has shown that, during rapid accelerations, they can pull up to, 2G during turns and deceleration, and that is the critical factor for them being so successful at hunting. Um, we also know some facts, and I say facts like inverted commas because these are things that people, I guess, just know in the anecdotally. If you ask anybody about the tail, people will say things like, the cheetah tail is high inertia or it's heavy. Um, we also hear often in wildlife documentaries or if you go in a game ranger park, sorry, a game ranger talking to you at a park in South Africa, they'll say things like it uses the tail as a rudder or a stabilizer. Um, but yeah, there's actually no definitive, study on and proving exactly what it's doing. And that's sort of where I entered my PhD in 2012, where I had this goal of, looking at animals, so looking at the cheetah, and then building, the new, most amazing agile robotic system. And then I would do this, building off and leveraging, biology in terms of having lots of whole body data, so data of like the entire kinematics and models of understanding the locomotion. But to my surprise and dismay, this data was non-existent, right? So there wasn't actually much known about how the cheetah is able to, perform these incredible maneuvers. So then I thought, what if we flip the script a bit, and what if robotics can actually give us insight into what the real animal is doing? So, can we use the techniques traditionally used in the field of robotics to tell us a bit more about how the animal is moving? And that's what we do in my research group, is we study animals through the lens of robotics. So we do lots of things which are traditionally done, in a robotics lab. So things like, multi-body 3D modeling and simulation. We do things like feedback control, to understand the sensory motor behavior of the animal. We use things like trajectory optimization or optimal control. More recently, looking at reinforcement learning to figure out what the best way to move is. We build, physical models, or, you can think of them as robots, to understand things like the spine or the tail and how that affects the motion. And then also we have spent quite a lot of my time, and I'll speak about it in my talk, on computer vision and state estimation. So that's basically like, how can we measure what the real animal is doing so that we can understand it better. Okay, so I started my journey and developed this robot on the right over there called Dima, which comes from a Sutu, which is a South African indigenous language called Leha Dima. The word means flash of lightning. Um, and the idea is that we built a car or wheeled robotic model to help us understand what an inertial tail, so having a heavy tail and flicking that around, what that could do for maneuverability. And yeah, I had the difficult job of watching lots and lots of wildlife documentaries and of cheetahs, and we sort of boiled it down to three motion primitives. And these are like three of the main tail motions. The one was motion in the roll axis, motion in the pitch axis, and then motion in the yaw axis, which I'll get to in depth now. So the first thing we looked at was the motion in the roll axis. So I'm sure many of you have seen this video at the top left there, of a cheetah chasing a gazelle, and as the cheetah turns, it flicks the tail in the roll axis. So that really got us thinking, and got me thinking of what's happening here. So one hypothesis I had was that during a turn, and a very high G turn, there would be a centrifugal force. So a force coming out of the center, trying to push and topple, a body moving in space and turning over. So, if that force got sufficiently large, so the turn is sufficiently tight, what would happen is the model will flip over. And that's what we actually did, is we built this robot with the tail. So this is the version without the tail. So you can see it falls over at 3.5 meters per second as we turn, and it's quite cool. It obeys physics as we expect. And then we added a tail with a feedback controller, and now we're able to turn, you'll see, at twice the speed as before. So yeah, really cool stuff is that it looks, it's flicking the tail in the way that we expect, based on what we see in the cheetah. The next thing is I took some cameras out at Cheetah Outreach, one of the cheetah breeding centers in South Africa. So was very close to Cape Town, and we saw something interesting which I didn't expect. Uh, so what the cheetahs do is during the enrichment, so for the exercise, they chase around a little piece of rabbit pelt or plastic around a track, and then there was a point where the lure, as we call it, like suddenly stopped, and what we saw quite often is as the lure suddenly decelerated, the cheetah would flick its tail up in the pitch axis, as you can see over there. So again, we thought like, could this be some stabilization effect? And it's exactly as we predicted in that, um, you know, as with the rolling, there's a braking force happening as a cheetah is decelerating, and if that gets sufficiently large, it can topple the body over. So if you imagine riding a motorbike or a bicycle, and you suddenly lock your front wheels, you'll end up like tumbling forward. So we tested this out in simulation. So you can see over there, that's the robot with the tail, and again with a feedback controller, just trying to keep the body level, and we're able to keep the body on the ground, which was quite cool. And again, we built a robotic rig. So this is a braking system that suddenly provided a deceleration rapidly. So now you can see with the tail, it doesn't topple over and is able to stabilize its body, you know, at twice the forward velocity as without the tail. So far the tails are proving useful for robotic systems. Okay, then the next thing, I found a video on YouTube, and apologies for the quality. It's really like the only one I've ever been able to find of this observation is we saw the cheetah doing an interesting thing where it's moving its tail in a combination of pitching and yawing. So kind of like in a conical, motion. You'll see it in the video over there. It's sort of like, and it also can turn it in a much longer uh, much longer durations of time. So you'll see over there as it turns, kind of moves it like in a cone in a circle with a tip. So again, here we went to mechanical modeling. I built a 3D tail model, and instead of in the previous studies, we hypothesized the feedback controller. So we said it was doing roll angle control or pitch angle control. We actually set it up as a optimization problem, and we said we want the optimizer to maximize the amount of roll on the body. Uh, and what was really cool is that the motion actually ended up being, the mathematically optimal thing was to do that conical motion, which is quite exciting. Um, so yeah, coming back to it, as I said, up until this point in my PhD, we said that the tail um, is often considered a counterweight, and that's kind of how I based my entire hypotheses around having this inertial thing that you can move around. But then in 2014, I was invited to a cheetah necropsy. So one cheetah had to be euthanized, and we actually discovered that the tail is only 2% of the body mass, so much lighter than we expected, and also much thinner and lower inertia. So what we then checked that this was true with about I think eight cheetahs in total, and this is indeed the reality. But what was interesting is that, like I said, when we did the autopsy and we looked at the tail, when we removed the fur, the tail was really skinny, like sort of like your finger width. But if you look at a picture of a cheetah, the tail is quite bulky, and most of that is actually made up of fur. So I had this crazy idea. What if the cheetah tail has all of this bushy fur? Could it be actually creating aerodynamic drag that the cheetah could be leveraging for stabilization? So we put a bunch of cheetah tails in a wind tunnel, and we actually determined that through the aerodynamics, the cheetah can create up to 40% more angular impulse on the body because of this aerodynamics and because it's moving at such high velocities. And in a sense, the effective area of the tail is doubled, without the penalty of having to carry around something really heavy, which kind of makes sense because this animal's really been optimized, for speed and weight reduction. And we did some experiments, so some on my sabbatical at Carnegie Mellon. We tried this on at one of the robots, and we were able to do aerial writing of a robotic model with a very lightweight tail. This is some work I've did with Aaron Johnson at CMU. And then we also took this a bit further, and we now said, okay, what if we had a really lightweight aerodynamic tail for Dima? And my student developed the system. So he did some more experiments on the cheetah tail pelts and designed this robotic um, tail, which kind of angles itself into the wind. So you can see here's the model with the aerodynamic tail. We then tested this out in the real system. You can see it topples over as you turn, if you turn at high enough speed, and here's it now with the with the with the aerodynamic tail. So really cool that it actually worked. Okay, so the other thing that we work on is trying to figure out what is the optimal or the best way to do a maneuver. And this is important for us to understand, for robotics, what, the energy optimal or the time optimal way to do a particular turn or deceleration. Um, but it's actually a really difficult problem because the cheetah, if you think about it, is a multi-body system. It's a hybrid dynamic system, which means it can make or break contact with the ground. And it's also really challenging, right? Because normally in optimal control or trajectory optimization, you can make assumptions like periodicity. So if you're doing a walking or a running gait, it should be periodic, cyclic in a sense, which, it adds a nice constraint to make convergence easier. And of course, if we are dealing specifically with aperiodic motions, we can't make that assumption. And the other thing is that you can see in this video is that we can't specify a contact order either. So like if you're doing walking, for example, in humans, it's going to be heel, toe, flight, up in the air, heel, toe, up in the air again. Whereas if you're doing a turning motion, you can see the cheetah is sliding. There's multiple contact points in touch with the ground. Like how do we figure out what the best contact order is? And I did some really interesting work on this with a guy, Larry Biegler, who's in chemical engineering actually, and we developed this contact implicit optimization method, which essentially, as part of the optimization through minimizing a cost function, it can also choose the contact mode, so it decides what the best contact order is for a hybrid dynamic system. So it's a lot of maths talk, but what does it actually mean? So it means that you can take a biped model like this one over here. So this is a model which has two legs and two contact points per leg. So there's a heel and a toe. And we can give it some basic constraints. So we say like start standing still, upright, end, some distance away, upright again at zero velocity. We then tell it, you need to obey physics through the multi-body simulation model. And then all we do is we tell it to minimize control effort, so minimize energy in a sense. We don't tell it anything about walking. We don't tell it anything about periodicity. All we do is we add these constraints, and what's incredible is something like this pops out of the optimization. So you can see it does a little heel toe, little skip at the end there. And all of that was not told. It's just the energy and I guess mathematically optimal thing to do, which is great. We've since extended this to handle partially elastic collisions. So my student, Stacy Shield, developed techniques. So we actually did like skateboarding maneuvers and so on as well. We also use this technique to understand and develop robots better. So one of the things that we hypothesize is that the cheetah and I guess quadrupeds that are running very fast aren't really finely controlling the force that they make on the ground. But what they are doing is really just trying to push off as hard as possible. So we thought, what if we designed a robot with an actuator that's, just it has a high force but not very well controlled with a one that you can control like a electric motor. So we combined a pneumatic piston with a electric motor for our robot called Kemba over here, and we with a very simple control policy of just turning on when it's on the ground and turning off when it's off the ground, we're able to actually create these acceleration movements. So you can see that's the robot doing a acceleration from rest into a bounding gait. Okay, but by and large, we have spent most of my time is on trying to understand like what the real animal is doing. So in my PhD, I showed that a tail is useful for a robotic model, and I've tested it on a model, a wheeled model. But what are the real animals doing? And of course, if this was a normal animal, or I should say domestic or easier animal to work with, I could just put it on a treadmill. But of course, this is not going to be the case. So what I've been trying to do really is everything that you can do in a biomechanics lab outside. And what can you do in a biomechanics lab, right? You can do 3D motion capture. You can do things like measure muscle activity. So how much are you, how much effort are you using? And you can do things like measuring contact force with a 3D force plate. So all of these things, my goal is I'm trying to do those outside with an uncooperative subject. Okay. So the first thing I looked at was how do we capture the motion of the animal? And most people think, okay, you just put a GPS collar, which uh, can capture motion really well and over long periods of time. But what they do essentially is they take this animal with all of the articulation, the spine and the tail and even the head and the legs, and essentially reduce them to, just a single lumped rigid body, or I like to say a flying axis system. So you can capture, what the animal is doing really well, like, it's turning and it's accelerating and all of that, but we don't actually know how it's doing that. And we don't know like where were the legs placed, how fast was the tail flicking, how much spine deflection caused that. We don't have any information on that. So I thought, okay, what if we put more sensors on the animal? So we developed this harness which we placed on captive bred cheetahs, which consisted of an IMU GPS, but also two cameras that faced backwards. And what they provided is they were looking at the spine and the tail as the cheetah was running. And then we fused that with my favorite sensor fusion algorithm, the Kalman filter, and we can then, reconstruct the spine and the tail motion as the cheetah is running. So you can see over there, we're able to do all of this reconstruction without um, any cameras viewing it from the outside. So if you ever wanted to see what it's like to ride on the back of a cheetah, this is some footage we have from the cameras. So this is not sped up. So it worked really well, but unfortunately, um, it didn't work well for all of the cheetahs, right? It was quite invasive. So after a while, they didn't really want to run with the harness on it anymore. Okay, then we approached GoPro, and they were excited about the project. They gave us a bunch of cameras, which we then put down at two cheetah sanctuaries in South Africa. So essentially, we had two stations where we could capture, from 6 cameras, the view of the cheetah as it was chasing this lure, um, during the enrichment periods. And over a period of 3 years, we collected quite a large amount of footage. You'll see over here the kind of stuff that we got. You can see these are captive cheetahs, so they really need to be coaxed into running. But when they do, it's really impressive. So what we ended up with was a multi-view, high-speed video of, I think, about 11 cheetahs over a period of 3 years. We even had one variant called the king cheetah, which is a genetic recessive gene that happens every now and then, where the cheetah's spots sort of blend and become almost stripes in a sense. Some of them had markers. I'll talk about that in a bit. But it was actually a lot more challenging than I thought it was going to be. I thought once I had all of these videos, I would basically have solved the problem of 3D kinematics of cheetahs. But So you can see like we captured at different times of day. You know, sometimes it's really dark, sometimes the sun is straight in the camera. We had different seasons. So in winter, the grass is nice and sorry, in winter, the grass is actually the same color as the cheetah in the bottom right there. Really, really tricky. We had, like I said, different cheetahs in the bottom left. We even had a king cheetah. Um, Angles and distances were completely different. So this is a completely uncooperative subject, so we couldn't tell it to do the cool flicking, turning in the middle of our motion capture arena. Occlusion is a big issue. You can see at the top right there, there's dust. The body itself, because it's so flexible, can actually occlude its various limbs. And then also importantly, we didn't have any markers. So if anybody has experience with 3D biomechanics, you know, you can put nice these like little round stickers or balls on a subject. We weren't able to do that. We were able to place some stickers on, I would say 10% of the cheetahs, but most of them did not have that. But then I approached some really smart people, Alexander and Mackenzie Mathis, who are now at EPFL. They developed Deep Lab Cut, and we extended Deep Lab Cut to handle 3D motion. So you'll see here how it works is that there's a neural network called DLC, which takes the views of an animal, so in this case a cheetah, and then the same network labels all of the joints, you know, the spine, the tail, the paws, the head. And then what we do is we take those 6 views that have been labeled by Deep Lab Cut, and then we can do it 3D reconstruction. But unfortunately, not because this isn't a marker-based system, you can see that sometimes we have outlier measurements. So they thinks the tip of the tail is that leaf. Um, it's also there's quite a bit of noise, so measurement noise, because we're not tracking you know, a defined marker. There is a bit of noise around each estimate produced. And so what happens is if you just naively do 3D reconstruction with that, you end up with kind of, I guess if you squint a bit, that looks a bit like a cheetah running, but it doesn't quite look like a cheetah yet. So then what we did was we combined the optimal control stuff I showed you previously with the Kalman filter work we did in the cheetah harness paper, and we then did a full, what we call a full trajectory estimation, where we use all of the noisy deep lab cut estimates. We use a 3D kinematic model um, and some temporal constraints on the motion, and then we can actually reconstruct a full 3D trajectory. So you'll see it looks really cool, is that we can now produce these motions that kind of look like they're captured inside a you know, a motion capture arena indoors. So this is from outdoor motion, the one that I showed you earlier on. You can see that's the cheetah and the looking and chasing the lure. So I was pretty pleased with that. And then we also released a full 3D data set. You can please check it out if you want to play around with it. So there's been some robotics work, so people you know, using it to train robotic controllers. There's also been some work on computer vision, people using it because it's a really challenging, tricky problem to test your algorithms on. So it's and it's all open source. You should check it out. Okay, but what's it doing with the tail? That's what I really was interested in. So we got lots of cool videos. You can see here, there's the tail as it's turning. There's also one here where as it's slowing down, it's flicking the tail. And then there's one here where I think you'll see it better in the slow motion. As the lure slows down, it suddenly like flicks up. So we did some pretty, I'd say, simple analysis, and we ended up with, I guess, a moderate correlation of acceleration to angular velocity of the tail, but it still wasn't, I guess, convincing enough for me. So one of the issues we had is that, like I said, the cheetahs are captive bred, so some days they don't want to run. We're also not sure if they are running at the same speeds, and because they don't have the same motivations as wild animals. So how can we improve things? Well, the first thing we can do is we can try and get more data. So many of the videos in a senior set actually can't be reconstructed because the cheetah's doing the cool stuff in the corner of one camera, and we need at least two cameras to see the entire cheetah to do full 3D reconstruction. So I had a crazy idea again. What if we could move the cameras and actually track the cheetah? So we developed a system where we had a camera on a motor, and what it did was it ran a neural network called YOLO, and it could then find the cheetah in the frame and then steer the camera as the cheetah was running past, and then do a 3D reconstruction on that. The other thing we want to do is, um, I guess with a set, we've shown that we can capture what the cheetah is doing really well, but we still don't know exactly how it's able to do that. And in order to do that, normally in biomechanics research, you need kinetics. So you need to be measuring force, so that you can figure out how much torque you require to create a particular movement. And this can help you understand things like loading on the joints or injury, which are quite important. So the next thing we explored was, can we estimate the kinetics from some of these videos that we have? So we worked with some guys at Royal Veterinary College to obtain, they had small number of force plate data for validation, and then we developed a system over there which essentially takes the 3D reconstruction and then fits a dynamic model to it, for which allows us to then estimate the torque and the forces on the cheetah as it's running. So this is an example you can see of the cheetah as it's running over the force plate, and then now we can use that to estimate the torque on the joints as it's running. Okay, but we didn't have a lot of videos with force, and what you really want to do is have the cheetah running on a force plate. So that's in a biomechanics lab, you would have typically have one or two force plates, and you'd have a test subject. And what you would do is you tell them, I want you to do the interesting thing on the force plate. So I want you to run, or I want you to jump on, land on the force plate. And they're typically quite small. They are, like maybe 0.5 by 1.2 meters in size, and then but the subject will do what you ask for most of the time. So the thing is, like, how do we get a wild animal to run exactly on our tiny 3D force plate? It's really, really difficult. So I thought, okay, what if we covered the entire area in 3D force plate, so a much larger capture area? So this will ensure that at least sometimes we get the cheetah landing on the 3D force plate. But a force plate is about $50,000 per square meter. So it's really, completely impossible. It just in terms of the amount of money it would cost. Um, so this I actually saw as an opportunity, because I actually ended up, this is my first patenting a new way of doing 3D force, using machine learning, which we've actually patented, and spun out a company to sell 3D force plates. So that's our force plate. The company is called the Cinetech. Um, and the force plate is, I would say, an order of magnitude uh, more cost effective than uh, similar products on the market. So this is how it works. You can run on it. You can see this is an athlete stepping on it, and we can get the 3D force profile um, at a much lower cost. Okay. The other thing we want to be able to do is to measure muscle activity. And muscle activity is usually done through subcutaneous needles or by surface electrodes that you put on a subject. But it's really tricky because, the wireless versions are expensive. You can only measure a finite number of muscles, and it's quite invasive. Like even on humans, you need to shave the subject, to make sure that you get a good signal to noise ratio. So again, I wondered if there was a way to do this remotely, and you can actually with what's called a millimeter wave radar. So one of my students developed a system where we use the radar and the small changes in the Doppler shift between the transmitted and received signal, and we're able to actually detect, as you can see, a really strong correlation we get between the radar phase and the EMG muscle, so the EMG of the muscle being contracted. Of course, this is still early days. The next step is going to be for us to explore how do we handle moving subjects, or can we track multiple muscles and so on? But it's still pretty cool, I would say, that we can now measure and we can track when a muscle is being activated without touching the subject. Anyway, back to the improvements. The other one thing we want to do is better data. So like I said, the captive animals don't have the same motivation as wildlife. But the challenge with wildlife is how can we do remote whole body skeletal estimation? And we pitched this crazy idea to Google, myself and collaborator Andrew Markham at University of Oxford, to develop this system, which essentially takes a high-speed telephoto camera and a long-range solid-state LiDAR and fuses those two to give us 3D kinematics from, over 100 meters away. And we developed the system you can see over there. And this is essentially how it works is on the right, you will have your regular high-speed video, and on the left, you'll have a 3D point cloud, which you now get from the laser through the LiDAR system. And the color is actually the reflectivity or the brightness, because one of the concerns we had was that is the cheetah going to actually, be reflective enough? And you can see there in the left that bright, fast-moving ball that it is in fact um, actually quite reflective. So we deployed this at a couple of sites, and one of which is the national park in South Africa called Kalahari National Park. So we got really cool pictures like on the left and cool videos, like you would expect from a wildlife expedition. But we also have really nice now 3D point cloud information, time synchronized and calibrated. So in the bottom left, bottom right, sorry, you can see that here's a giraffe. This is about 120 meters away. So not only do we have the video, but we also have now the depth for each of those points on the giraffe, and we can now fuse that to give us 3D kinematics. We also managed to catch a cheetah mother with her 3 cubs taking down a gazelle, which was quite cool. You can see on the left there is the RGB, and on the right we have the LiDAR, so the 3D points as well. Okay, how do we combine these? Really tricky because there's the focal length changes as we zoom. But yeah, this is some work my student has done where we can colorize point clouds using a technique called self-supervision. And now using this, we can do 3D kinematics. Like I said, we can do, here's the skeleton of a skeleton being tracked of a lion. We can also now, because we can do very long range 3D capture, we can capture group behavior. So get a bird's eye view of a group, sort of doing group dynamics. This is a herd of springbok at Kalahari National Park, and you can see how the different individuals are moving with respect to the herd. We can even detect some behaviors like there was some sparring happening. We can track individuals as well. So this would be interesting for ecologists to studying group dynamics. And then also very interesting, we were able to, we found a few lions sleeping on the side of the road, and then using the LiDAR signal, we were actually able to extract the motion of the chest, and we can then detect the breathing rate of the lion. So you can see there's some like panting happening, and then yeah, the normal breaths happening. So really cool and surprising use case. Okay, so what's the next challenge for us? So if we look at deep learning in computer vision, it's really doing incredibly well. I'm sure most of you know that there are so many amazing models that do lots of the heavy lifting for you already. And there's two reasons for that. The one is the availability of GPUs, so graphics processing units like um, NVIDIA's systems. And the other one is the availability of large open data sets. So on the right there, you see something called Human 3.6M. That's a very large scale data set for human 3D motion capture that many 3D algorithms and deep learning models for humans are actually based on. And there's many data sets like this. But this is really challenging to obtain for wildlife, right? Because like I said, we have an uncooperative subject, there's occlusion, varying backgrounds, and then also if you do it inside a lab, doesn't have the same motivations as you would. So the real thing I think on the critical path is data sets. So one of the ways I thought we could do that is by developing a mobile way of collecting ground truth and data. So we developed what we call the multimodal sensor suite M2S2, which consists of a parabolic microphone, a LiDAR, a thermal camera, high-speed camera, an event camera. I'll show you in a bit what that is, and then the radar that I showed you previously. So in event cameras, these really new technologies that are essentially asynchronous sensors that work similarly to your eyes in that they don't send back the entire frame, they only send back the pixels of light that have changed. So you can end up with these, you can see these really high frequency motions being detected. And also it works really low power because if nothing is happening, it doesn't send back any information. So there's no motion, no data is sent. So we developed this system, like I said, and we tested it at again 2 cheetah sanctuaries in South Africa. So you can see here we're able to capture multimodal data of cheetahs. So we have the RGB, the LiDAR, the thermal on the top right. We have the radar bottom right. We also have the event camera in the middle. You can actually hear the sound of the cheetah purring. So this is a cheetah doing a run. In slow motion. So you can see, yeah, we now have these synchronized data, which we can then use to do new things, right? So we can do 3D pose estimation at night. So we can take our thermal image and combine that with our 3D LiDAR and then be able to reconstruct 3D motion in complete darkness. We can also do things like combine the RGB video with the event camera to be able to detect, much, much higher motion, much higher speed motion of animals. So yeah, that's sort of it in conclusion. Studying, I guess, wildlife cheetahs specifically is quite challenging, and I would say often requires a multi, you know, sort of attacking the problem from many angles. I like to think of it as the space race because it highlights the shortcomings of many of our current technologies, but also drives us to innovate and come up with new ways or reimagine ways of sensing or control or simulation. So yeah, these are my students and my sponsors and my collaborators. But thank you for your time. I hope you enjoyed the talk.
Thanks a lot, Amir, for this fascinating talk. It was really, really interesting. So we already have some questions on the chat, but I will start with just one of mine. Like, I was wondering, like, because your results suggest that the tail really has a principal role inside the maneuver. And I was wondering if you had the chance, for instance, to observe this hypothesis, like in a cheetah that has been injured and that lost the tail, for instance, and see like whether the maneuver are not possible for this cheetah anymore, or if maybe they are actually going for another type of strategy in order to compensate the movement.
That's a good question. Yeah, unfortunately, we haven't been able to do that. But I think it would be great if we were able to, um, find a cheetah with a, small tail or something.
Yeah, yeah.
Or I mean, another idea I had was like if you could, I guess anesthetize like just the tail
Hmm.
and see if it was, but yeah, it's really difficult to get the
Yeah,
ethics to
yeah,
do
yeah.
that kind of stuff because it's an endangered animal. But yeah, what I should say is like I think the tail, I mean, I don't think that the tail is like make or break, but I do think the tail would benefit the cheetah, sort of like give you that extra 10-20% chance of catching
I see.
your prey. Because I mean, animals are extremely robust, like and adaptable. It's possible that a real animal would figure some other way out without a tail.
Yeah, okay, I see. Thanks for this answer.
Should I stop sharing, by the way? Sorry.
I mean, it's up to you. Like, you can like just in case someone wants you to go back on a slide. It's maybe
Right.
good if you continue sharing. We had two questions from two different persons that I would say that are going in the same direction. I mean, hopefully, like if I understood them. We have Daniela Kinoshita who is asking, have you tried to use or mix the cheetah body motion with other felines that also have these traits? And we have David McCluskey who say, do you think that this work applies to the running dynamics of other big cats, or is the cheetah a special case?
Mhm. That's a good question. Um, so wait, can I just, what was the first one again? If
So
I,
the first one was, have you tried to use or mix the cheetah body motion with other felines that also have these traits?
Mm. Yeah, so I guess what I should say is that there has been some studies done on domestic felines where they had them walking on sort of a thin balance beam, and those ones they were able to anesthetize the tails, and they showed that there was a strong correlation of falling off the balance beam when they didn't have the tail active. So it is, in cats, it's shown to be quite important. Um, in terms of other felines, yeah, I think the cheetah is a special case because I think it's one of the few cursorial, hunters where it's chasing down its prey as opposed to stalking and pouncing like the other big cats. So I do think that that makes it a special use case. That being said, though, I think maybe this links to the second question is that I think that other cats are using their tails and possibly for a related reason in that if you watch snow leopards um, running, coming down the mountain, actually, they use their tails a lot, right?
Mm,
During flicking for balance as well, and their tails are also quite bushy. So I think that it's possible that they are also using it for stability. I did also saw I see a video. Sorry, I saw a video on YouTube once of I think tigers that had been for some reason uh, bred in Africa and they were hunting. And they showed that when they were chasing an ostrich, I saw that they also flicked their tails like
mhm,
that. So my next experiment, I would say, is to investigate because I think that what makes the cheetah so special is that the front and the back of the body, um, when it's because of the flexion of the spine, need to be stabilized relative to one another. And I think when there's a maneuver like a turning motion, I think the front and the back part of the torso kind of like roll out of place. And I think without the tail, it would take a longer time to, bring or more effort from the trunk to bring the back part of the body, back in line. And the hind limbs are where the thrust comes from. So you want to kind of always keep that in the same direction that you're running. So I think that that is the key to all of it is the fact that they have the spine. It's kind of like interlinked to the tail.
okay, yeah. Actually, Lala, we just received a follow-up question on our previous discussion about if we could maybe impair the tail in order to see what would happen. And it's Laure Cochard who is asking, like, do you think that it would be possible to maybe add some weight to the tail for a short period of time, just in order to see how the cheetah is adjusting the movement? I imagine that
Yeah,
there are some ethic also, like
very
limitation here. Yeah,
tricky. Yeah, yeah, very tricky. I mean, I haven't considered that. It's something to, but it's difficult because the cheetahs that we can do that on would be, or possibly do that on, would be the ones that are captive bred,
yeah.
and they are not running at like the same speeds as the wild ones. So I mean, I think the fastest we've measured the captive ones is like 16, 17 meters per second,
Okay.
and what Alan Wilson's group found is that they run in hunting, like, 22, 25 meters per second is where they're sitting. So I think it would be tricky.
And is it's only a difference of speed, or you also observe difference of maneuver between the one that are in captivity and the one that are in the wild?
Yeah, two points on that. Yeah, so the first is like so they're captive, right? So they know the track and they
Yeah.
know that so they know that the law is gonna come back around. So more often than not, they kind of like don't they don't turn as sharply as you would think because they know that where it's going to go next. Um, the second thing I should say is that what I've observed anecdotally is that the younger cheetahs use their tails a lot more.
Okay.
So the sort of juvenile cheetahs that are, coming of age, and they flick their tails a lot, and but they also tumble and slide and fall a lot. Um, and I think maybe the older ones are, kind of like a bit more clued up on how the kind of bodies work in a sense, whereas if you think of it, the younger ones are still figuring it out, so they're going to use more actuation of their tail, maybe unnecessarily so.
Okay. We just received like a funny comment about this idea to put some weight on the tail by Denuneri, saying that she imagined that if you were doing that, you will just end up with a house cat that has something stuck on the tail, just kind of turning around. We also received a series of questions from Bastormata Forever that are more technical. I will go one by one because there are several. The first one was like if the collar measures the cheetahs only when they are running or full time.
The ones that we developed, the harness, I
Yes,
guess.
yes.
Yeah, it was only when they were running that we were able to reconstruct the motion. Yeah, because it was too cumbersome. It was quite challenging to get it on.
Hmm.
Like we had to acclimate them, just putting it on for a little bit and then taking it off, and then for longer and longer periods of time. But eventually, I think they just all got over having this thing on them.
Yeah, okay. So the second question is about the harness too, like, and so like Bastormata Forever asking, how can there be accurate measurement of the harness on the cheetah's back when the only part of the body that doesn't move when they run is their head?
Yeah, so no, the harness is moving around a lot. Yeah.
Okay,
So
yeah,
that's why we have an IMU and a GPS on the harness itself.
okay, yeah.
Yeah, so we fuse all of that information. So it's like observing the tail and the spine from a camera that's moving as well.
Mm-hmm. Okay, but then, and I guess like because the last question is also a little bit related to already what you said about the age, at least because so Bastormata Forever is asking if the age, size, and gender of the cheetah could actually like change the result of tracking this type of. I mean, like if you can observe different things. I think you already say that, for instance, the youngest one will use more the tail, right?
Definitely. Yeah,
Yeah,
I mean, I would love to do like a long-term study and see how they learn to do different movements. That would be very cool.
yeah. So we also received, and actually that's a question that I wanted to ask too from Laure Cochard, who is asking if you are interested in applying this research, like and this line of research with robotics to other animals than cheetah.
Wait, so studying animals, other
Studying,
animals?
yeah, studying maybe the movement of other animals using robotics.
Yeah, definitely. No, definitely. I'd definitely be interested in studying other animals. I mean, we've done some work with canines, um, but we haven't actually done applications on other animals. But I would be very interested in anything that moves
Yeah.
fast. Is interesting to me.
Okay. And I maybe have actually a technical question that is going a bit in the same direction because I was quite interested about this tool that you show in which you can determine the frequency of movement of the belly of the lion, right?
Yeah.
And I was wondering how sensitive is this tool? Is it something that you could consider using with like with smaller animals? Let's say in my case, for instance, I am studying zebrafish larvae. Do you think that it's something that I would manage to actually use in order to see, for instance, hyperventilation or that type of things?
Okay. Yeah. So there's two things there. So the one is the system that we did the lions with is the LiDAR. So that's actually meant for long range
Okay.
capture.
Yeah.
So we're talking like it can actually go up to 500 meters with the resolution being 1 centimeter. So I think you kind of trade off resolution with the range of capture.
Uh-huh.
So I think for the lions it's fine, but for other animals, like for example your zebrafish larvae, I would rather use something, you know, much closer, like a time of flight camera would work nicely, or even a radar, right? So the belly motion that you speak about is quite a consistent frequency, and I would do something like with that frequency modulated radar that I showed with um, the Doppler shift actually changing, you could detect. And so we've done things like that with respiration
Yeah.
rate in canines and cheetahs as well, which I guess is unpublished, so I wouldn't want to show it yet. But yeah, so you could definitely do it with a radar.
Okay. Okay. Very good to know. So yeah, like, I mean, people, like, if you have more questions, like, do not hesitate. We still have a bit of time. I saw that it has been posted on the chat, but like, yeah, indeed, like, we invite you to actually go through the Discord and go through the website, because we have the link to listen the Meet the PI with Amir, because we had a very long discussion in which Amir is explaining us actually how he ended up doing this line of research. It is particularly interesting and inspiring for the youngest of us. So like, I think it's super nice if you guys take the time to listen it. So I don't see any more questions at the moment. So I would say that we can end up this talk. Thanks again, Amir. That was really nice.